Okay, so next presentation, the second one and last one for the testing session. So Jan Romanick is going to talk about the difficulty of testing every possibilities.
Hi, so I think at this point most people in the room know who I am. Me and Romanick from the OpenGL group at Intel. I'm going to talk about testing uniform buffer objects and standard 140 layouts. And sort of, there's a whole bunch of problems surrounding this. I'm going to talk briefly about what the different problems are and how we use a little bit different sort of testing strategy to try to tackle those problems and improve the situation a bit. And found that the whole thing was actually quite a bit more than I thought it was. And I didn't have high expectations going into it. So when uniform buffer objects were added to OpenGL some years ago, around OpenGL 3.1 kind of time frame, so quite a while ago at this point, there was a standard ABI added called the STD140 packing, which basically defines, given a particular uniform block declaration, you can just look at that and know where the driver is going to put every single field of the UBO. So you can build your UBOs, declare it with the standard 140 layout, and then just not have to ask the driver where anything is, load all of your data into it, and just go. There's 9 rules in the spec. They're in the extension spec, and then they're in the 3.1 spec that define like what the base alignment is of all the different types and how structures get padded out and how what the array stride is for things and how matrices are laid out and stored in memory. But it turns out that implementations are really, really bad. In just this recent July, I fixed a whole big pile of bugs that were found by running an updated version of the Kronos ES3 test suite. Over the last year or so, there was around 2,000 new tests added that were developed by draw elements. So there was a series of 12 commits that fixed a bunch of really things that we should have caught in our own testing. And so you can look at that series and see what some of the dumb things are. But we're not the only one. So I talked to Christoph Riccio. He's the guy who runs the G-Truck site. He also works at Unity 3D on their engine. I was talking to him at SIGGRAPH a couple of months ago, and he just told me flat out, we just can't use UBOs because everyone has so many bugs in their layout code. Nobody has the same bugs. If we have any kind of, if they have any kind of non-trivial UBO, each vendor is going to lay it out differently, even though it's standard 140 packing. There was while I was working on this, I found a Twitter quote, kind of disparaging about the state of things, and these kind of sentiments, if you spend just a little bit of time going around the OpenGL.org forums or other game developer forums, these sentiments are echoed everywhere. So, just kind of looking quickly at one of the examples. So you have a structure that has has a float and an int. You have a UBO that has a float and then has an instance of that structure in it. So rule 9 says, blah, 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 base alignment of the structure is whatever the largest base alignment is of one of the members. And it seems that's where everyone who is implementing UBOs in drivers stopped reading, because they would put the base of that structure at offset 4. They didn't finish reading the sentence that says rounded up to a vec4. That should be at offset 16, but one major vendor, I don't remember if it was AMD or NVIDIA, puts it at offset 4. Like, just read. So even after I had gone through and fixed a whole bunch of things in our implementation based on the conformance tests, I had this just kind of nagging voice in the back of my head saying, you fixed a bunch of stuff, but There's probably more bugs there, and we have a bunch of additional functionality coming along soon. Support for double precision layout rules, because a bunch of the places where it says, basically almost all of the alignments end up getting rounded up to VEC4 alignment, but then if you have double precision, then you have DVEC4s that have 32-byte alignment. So a bunch of the alignment rules change. Arrays of arrays support is coming. And then when we add support for shader storage blocks, we'll have the new standard 430 packing rules to apply. So there's a whole bunch of pieces of functionality coming into Mesa that are going to just have to change a bunch of our layout code. So I thought, we need a stronger testing strategy. We need something better. And just sitting down and trying to think, what are all the cases, what are all the things that could go wrong, and then write a bunch of test cases for that, which is, generally what we do with most things, just wasn't going to cut it. So I took a different kind of approach and applied some techniques of random search algorithms. And I'm going to spare details. There's a white paper that's linked from the XDC site, from the wiki, where I talk quite a bit more in detail about why these kinds of techniques work and why people use them. But the general idea is make just an infinity of tests by generating a random or semi-random uniform block, and as the block is being generated, apply the rules in the test script to know where each field should be, and then generate probes that query through the GL API everything about every field that can be queried through the GL API. What the offset is, what the type is, what the array size is, stride, et cetera, and then generate a shader that will probe every one of those, or actually not quite every field. There's another bug about that. Anyway, I'll get to that in a second. That will probe all these fields, put some data in, check all the fields. So make sure not only that the driver says, yes, I laid that out the way that you think that I should have laid it out, but then also, check it that, yes, if I put 6 at this location and I read that location, yes, it got 6 there. Because we had some bugs with that. So the reason I don't probe all of the fields is the way that the tests are generated, and there's going to be a live demo at the end, and I'll show some of the tests. You end up with a bunch of foo equals 6, pass equals false. So there's a whole bunch of these really, really tiny basic blocks, and our register allocator hates that. And so there's a bunch of these tests that, so I gave up on proving all the fields when I had to kill one of the tests after it had been taking 25 minutes to compile, because I got tired of waiting for it. Because it was just all the liveness analysis that you could ever care to have happen. And then on the flip side, this found a bug in AMD's driver where in a standard 140 packing, if a shader doesn't access a particular field of the UBO, you're still supposed to be able to query information about that field, and they say, nope, you wasn't using it, that field's not active, I'm not going to tell you anything about it. So we also used to have that bug. That was one of the things that I fixed in the previous 12 patch series that I mentioned, so I can't disparage at them too much. So then in addition to this, so these scripts, these tests that are sometimes will generate a UBO that has a few hundred fields in it. You run the generated test and it says, nope, it failed. And now you've got this giant pile of stuff and okay, what part failed? So there's a second script that takes the generated test and tries to trim it down. And so basically what this does, because it was the much easier way to implement it, is there's a bash script that in a loop runs the Python script that picks a random of the UBO and removes it, rerun the test and see if it still fails, and just keeps doing that over and over again until it can't remove anything else, and then says, here's your minimal test case. And I'll show some of that in action in the live demo. So this has been really, really successful. I found 6 bugs, in addition to the bugs that were fixed by the 12 patch series back in July. I found 6 additional really weird, obscure bugs that someone sitting down and just writing tests by hand would have ever tested these cases. There were things like, if you have a structure that contains an array of structures, and that inner structure is only 8 bytes long and it's preceded by a single 4-byte field, things aren't laid out correctly. Like really, really obscure things that, you know, just let the test generator start generating tests and, you know, go to bed at night and get up in the morning and check and see what it did. It will come up with that stuff. But, you know, even an army of 100 interns would not have come up with that in a summer. And there's a whole big pile of bugs that I found. I did a lot of this development going into this thinking, you know, generally NVIDIA's driver is pretty solid about stuff, so I'll do a bunch of my development of the test generator against their driver so that I could be sure that the generator is correct, and I found just as many bugs in their driver as I found in ours. And in the very, very little bit of testing that I've been able to do on AMD, they seem to be in just about as dire shape. So it's a pretty terrible situation. So let me switch over to and do the live demo real quick. So there's a simple script. So here's the script that basically runs the tests overnight, and it runs the generator to generate a test. You can give it a description of what your driver supports, GL version or list of extension strings or whatever, and it will pick some random thing that you support and generate a test that tries to exercise a bunch of that functionality. Runs it through Shader Runner. I had to add a few features to Shader Runner. Shader Runner didn't have the ability to, say, probe information about UBO layouts, so I added that. I also added the ability, when comparing floating point values that are stored in the UBO, I wanted to do bit exact comparisons, and you can use some GL operators to do bit casts between floats and ints, so I could do the bit exact comparisons using that, but Shader Runner didn't have a way to say, no, I want this actual value for my float, so I had to add that. It just runs, so then it runs it through Shader Runner, and if the test passes, it moves it into the pass folder, and if it fails, it moves it into the fail folder, and it keeps running until you get 1,000 fails, because at that point you've generated plenty of work to do, figure out what the hell's wrong with your driver, so it just stops burning CPU and wasting electricity at that point. So I can let that run. And it's very exciting to watch. So eventually it will find a failure. I patched out, I reverted one of the fixes, so eventually it will find a failure. So then the other script is the trim script. So there's a separate piece of Python code that will trim an existing test that's been generated. And so it just runs this in a loop until it goes 100 times without being able to reduce the test, and then says, okay, here's your minimal test case. So I had run this earlier, and I have a test. What was it? So here's one of the tests that gets generated out of this. So up at the top, it just does a raw dump of all the Python data structures, and this is what the trimmer reads in and uses to be able to regenerate the stuff out, and then it generates out actual GLSL code. And one thing that I ended up spending a lot of time on was in the UBO that it generates, it pretty prints the thing out so you can see exactly where this thinks every single field should be and exactly what its layout is. So if you're, it's very useful when you're trying to debug, like, well, my driver says it's at this location, what does it think this stuff should be laid out? And then, you know, you can go back and compare that against the set of rules in the spec. And it was useful both for debugging the script and for debugging the driver, and it's very, very verbose. And then the giant pile of test, check all the fields stuff, and then all of the introspection bits to just probe every single field. And are you where you should be? Are you the type that you should be? Et cetera, et cetera. So if you run this, and I'll go ahead and and it comes back and says, fail. Okay, quick. Where's it broken? Right? It's madness. So then you can just run the trimmer. And what was the original one? Fail. And it will run through and say, okay, I'm trying to gut out all these fields, and it'll run and kind of do its thing for a while, and then at the end it says, aha, I ran a whole bunch of times and now I couldn't make any more progress. So now we can look at the trimmed test, and now it's a lot more tractable, although then this one didn't. So because it's doing things randomly, it doesn't always get an actual minimal test case. So I know that this could have reduced the size of this array, and it usually does. But just looking at like the shader comparison code that's left, it's a lot easier to track down. So before, when I ran this, what was the original trim.keep? So it did trim it down a bit, trim it down even smaller when I ran it before. So it's, you know, it's a non-deterministic process. It's one of the sort of double-edged swords about randomized searched algorithms in general, is that you're kind of, they tend to make this performance correctness trade-off. Yes, I can give you an answer fast, and statistically it's a really good answer, but sometimes not exactly correct. There's a lot of really interesting work on like solving the traveling salesman problem in linear time, but you know, maybe you didn't get exactly the optimal answer, but you didn't have to wait until the end of the universe to get it. So then, you know, looking at this set, it does very long to be able to track down the bug in the driver when you've got a minimal test case, and then you have a minimal test case that you can just add to the test suite. And it still hasn't found. So if we let this run long enough, it will, oh, you know what? I'm running it on. Yeah, all right, all right. Okay, there it goes. So there, so it found, so here's the link test that it found. And the failing test looks pretty similar to the other failing test because they have they're tickling the same bug because I only reverted one patch. And so then also it dumps to the pass directory all the tests that actually pass. So the useful thing about that then is once you go back and fix the bug in the driver, go rerun all the pass tests and make sure you didn't, you know, break one of those. Okay. Okay, so there's a white paper, and then all of the test scripts are currently in a branch of my Piglet directory, or my Piglet tree. I sent these out to the Piglet list a few weeks ago for review. I got a bunch of review comments primarily about Python style and how to do things better with the Python, because I still write Python like it's C. And yeah. Well, whether I should or shouldn't, it's as I do. The thing that hasn't really been solved yet is how do we want to integrate this into regular Mesa testing? I mean, having it run as, a loop of, okay, now if in your Piglet test run, you have an hour of it generating random tests and running those. No. It's one of the other scripts. So the process is also, there's a, what did I call it? So the tests can also be kind of directed. The random generator will generate the tests that have some specific complex element in it. So in addition to having those be random, you can instruct it to generate tests that have a specific thing. So for example, we'll look at this one here. This will end up generating a test that declares some field in the UBO to be row major, to be an array of a that contains an array of and this is going to iterate through in the loop of each possible matrix type. So that in this case, we know that we're hitting arrays and structures and all of the matrix types as both row major and column major, and make sure all the things get laid out. So in this, it generates this kind of fixed set of tests that are known kind of problematic cases, but each time it runs, they'll be a little bit different because it's going to generate this. There will always be an array of structures containing an array of matrices, and then the structure and the top level UBO will also get filled in with some other random stuff just to make life interesting. We filled in with a bunch of members of some basic GL types. But it's not clear, is that a good way to, is having a couple hundred of these tests, do you pick a set of them that got generated once, or do you have it each time someone builds, regenerate a different set of tests? What's the right thing? And there doesn't, I don't know, all of the answers seem unsatisfying. So that's kind of the open question that is a big part of the reason why none of this has landed yet. I think that as new functionality gets added that affects UBO layouts, like the double precision code that Dave and others have been working on, that when they think that's done, okay, we'll go ahead and run the random generator with support for probing doubles turn. Let that run for a couple of days and see if it finds anything. But that's not part of the regular Piglet testing process. Okay, so that was all I had. Any questions? Yes?
Did you capture all of failing tests for all the drivers you tried and save them?
I haven't. I'm able to. Yeah, and so that was one of the other thoughts that I had was find all the places where people fail, generate the minimal test cases from those, and just add all
those
of
in Piglet.
Yeah, and just add all of those. The script to do the trimming was a relatively recent addition. I did that like a week ago, and I haven't really done very much running on other drivers since then. But yeah, that would, and that's actually kind of the most, the least unsatisfying of the ways to integrate this into Piglet, is just find representative cases of all the places where we know someone has failed once. Way in the back. We're going to make him get all his exercise in running the mic back and forth. So now one of you guys, you're on next.
There exist other test case minimization tools that would avoid that job of trying to really generate a minimal one. Delta is the one that comes to mind. I'm trying to remember where that actually lives. Delta.tigris.org.
Okay.
So that might be, rather than trying to improve the Python script to try to minimize the test case, that might do better at generating something truly minimal, because then when you're putting something into Piglet, you're fixing exactly this one
Right.
class of layout bug. Just something to consider looking into for making this more
Okay.
industrial strength.
Yeah, I'll look into that. What did you say? Where did you say it was?
Delta.tigris.org, Tigris.
Okay. I'll look into that. I mean, right now, even in the cases where it stuck in a local minima, it's still a greatly minimized case, and still, at that point, before I was doing all of the test case minimization by hand, kind of doing when I had the so when I had the test like this, basically what I was doing is going through the giant blob of comparisons and kind of doing the binary search to find the comparison and then once I had found that, go through and just start deleting stuff out of the UBO until that comparison didn't fail anymore, and then kind of working from there. But having even getting a not quite minimal test case, having it automatically do it was like, oh, I should have thought of this weeks ago.
Yeah. My other question would be, when looking at the classes of bugs that this is exposed, is there some particular part of the spec language particularly tricky, and that maybe standard 150 would make
Right.
something that's easier for implementers
Well, so
to
there's
do
two
correctly
there's
up
two
front?
things that people have generally screwed up. One is not propagating. So by default, matrices in OpenGL and GLSL are column major, but you can decorate, and I'm sure that there's a. So you can. Okay, so there isn't one in this particular case. You can decorate your matrices and say, no, I want this one laid out in memory row major. And in various of cases, most often if the matrix is somewhere in a nesting of structures, people will just forget that the matrix was row major and, oh, I'll go ahead and lay it out column major. Or the great thing that we had a couple different varieties of instances of is the API will say, yes, it's row major, and we'll have everything at the correct offsets, and then the lowering pass that actually generates the loads forgets that it's row major and generates the loads as though it was column major. Those were fun bugs. And there's a few different places in the spec, like the place that I highlighted where it says, or round it up to the alignment of a vec4, and people just only read half the sentence and missed that. There have been a lot of those, both in our driver and in NVIDIA and AMD's closed source drivers.
So neither of those really sound like things that you could spec out of existence. Like if you had a secondary thing, you're not going to want to lose row major versus column major.
Right.
Okay.
And it's just, it really is just people not reading the spec. And there's not that many rules, for crying out loud. Yeah, they're different in C, and they kind of reflect how a lot of OpenGL 3.1 vintage GPUs work, right? Like, for example, our driver really doesn't want to do loads so if you have an array of something that's smaller than a vec4, our hardware really doesn't want to do, those unaligned array loads from somewhere in the middle. So we really want to have, even if floats, we want each float, the array stride to be 16 bytes. That's way easier for us to load. And so it just kind of reflects the hardware. Anyone else? Okay.
Very well.
Thanks.
Thank you.
So, so have you encountered a bug where some previous tests has corrupted enough state in the driver so that all the next tests also fail?
No, and the reason is that these are just their shader runner tests. So each test gets run individually, and then the program terminates, and all the GL state gets torn down, and then completely restart everything up from scratch. Yeah, so there isn't really any opportunity unless you actually crash the GPU. But you know, GPU reset works pretty well these days, so even in those cases, you wouldn't notice it so much.
Okay. Thank you again.